Hello everyone, let me introduce myself. I am Facundo Carballo and today I will explain you all about concurrency and synchronization mechanisms in Golang. In this complete guide, we will see how concurrency works in Golang with Goroutines, how to run multiple Goroutines at the same time, and how to synchronize those Goroutines to communicate with each other and work in a concurrent way to do what we want to do in our programs. After that, we see all the synchronization mechanisms that allow us to synchronize all of those routines that we execute. We will see that it's not enough with just applying concurrency and synchronization mechanisms, because concurrency brings us a lot of problems, a lot of concurrency problems, such as race conditions, deadlocks, and starvation. But all of those problems we will cover up at the end of this video. First, we have to learn concurrency and synchronization. After that, we will cover concurrency problems. And before we start with the video, I want to tell you two things. First, all the code that you will see here on this video, you will have it on my GitHub repo. The link to that GitHub repo will be on the description of the video. I recommend you that you have it close to you, this GitHub repo, because it will help you to understand better all the things that I am explaining here on this video. And second, if you like this kind of videos, please hit the like button and subscribe to my channel, because that will help me a lot, and it's just 2 buttons. So hit these 2 buttons, please. Come on, it's free. With that all said, I will let you with the video. Okay, so first we have here a diagram where I try to show you some examples of programs that need resources. And here we show how to get those resources in a sequential way and how to get these resources with concurrency. Okay, first of all, we have here a main program, in this case in Golang, but could be in any programming language, but here is on Golang. So first of all, we have a program without Goroutines. This program needs 2 resources, the resource A and the resource B. For this program, first we'll call to this API, for example, and we will wait for this resource. And then when the program gets that resource, we'll start another API call to get the other resource. Imagine that the resource A, for example, is the price of Bitcoin on some particular exchange, for example, the Binance exchange, and the resource B is the price of Bitcoin, but in other exchange, like KuCoin. And this program wants to compare each price and determine which price is cheaper, in what exchange I can buy Bitcoin cheaper. So that is the main thing of this program. So here, this program will request to the API of Binance the price of Bitcoin, and we'll be waiting for the response of the Binance API. Once the program gets the price of Bitcoin, start to execute another API call to the KuCoin API. So this program make another request to that particular API of KuCoin, and then the program will be waiting again for the price of Bitcoin on KuCoin. Once we get the 2 prices, the program can compare each other and determine which price is cheaper, so in which exchange we can buy Bitcoin, for example. But we can do it with Goroutines, applying concurrency, and that will be saving us a lot of time, a lot of dead time, because when we are requesting data to some API call, we have to wait some time. It's just milliseconds, but it's time. It's time that we can save applying concurrency. So in this case, for example, if we apply concurrency in this particular case, we have a main program that will be forked into subprocess and into Goroutines. The Goroutine number 1 will be focused on get the price of Bitcoin on the Binance exchange, and the Goroutine number 2 will be focused on get the price of Bitcoin on the KuCoin exchange. And then when these 2 Goroutines get the prices, we'll return to the main Goroutine, to the main program, and then the program can compare the prices and determine which exchange is better to buy Bitcoin. But with this schema, we are saving a lot of time, a lot of dead time. in each request. We can see this better here in this other diagram. Here we have the timeline of this program without concurrency, without Goroutines, where we have our main Goroutine, and then we will make a request to the Binance API, and we will wait for the price of Bitcoin. So this time we get the price of Bitcoin on the Binance exchange. Once we get that, well, we can start to getting the price of the Bitcoin in the other exchange, in this case KuCoin. And well, we have some time to make the request, another time to wait for that particular price. And well, when we have the two prices, the main Goroutine will do something. For example, compare these two prices and determine which exchange is better, is cheaper. And here we have the timeline of this program, but using concurrency, applying Goroutines to this program. So we have the main program, the main Goroutine here executing, and then we fork this program in two Goroutines. One Goroutine focus on get the price on Binance, and the other focus on get the price on KuCoin. So the first Goroutine executes and make a request to the Binance API, and this Goroutine gets blocked because this Goroutine needs the price of the Bitcoin in the Binance exchange to continue executing the Goroutine, but this Goroutine don't have it. So the operating system knows that this Goroutine have to be blocked because it can continue executing. So block this Goroutine. In this case, in this particular moment, another Goroutine or another subprocess or another process that the operating system have and has all the resources to execute, for example, the Goroutine number 2. So the operating system put the Goroutine number 2 to execute. And the Goroutine number 2, well, do some stuff and then make a request to the KuCoin API to get the price of Bitcoin. And in this case, in this particular moment, the Goroutine number 2, it's blocked too, because this Goroutine needs the price of Bitcoin on KuCoin to continue executing. So the operating system knows that this Goroutine cannot continue executing, so we'll block this Goroutine until gets that particular resource. So the operating system quicked this Goroutine and will try to put another process to execute that have all the things that this process needs to execute. For example, in this particular moment, when the Goroutine number 2 is making the request to the API of KuCoin, maybe the API of Binance already returned the price of Bitcoin to us. So when this Goroutine number 2 is blocked, the Goroutine number 1 has all the things, all the resources that this Goroutine needs to continue executing. So when this Goroutine gets blocked, the Goroutine number 1 came back to execute and will finish the Goroutine because this Goroutine already have the price and finish. Meanwhile, the Goroutine number 1 is ending. The API of KuCoin maybe already returned us the price of the Bitcoin in this particular exchange. So when this Goroutine ends, the Goroutine number 2 already has all the resources that they need to execute again. So the operating system will put again this Goroutine to execute because this Goroutine have all the things that they need to execute, because this Goroutine have already the price of Bitcoin on the KuCoin exchange. So here the Goroutine number 2 will end, and then the main Goroutine will execute again with the price of Bitcoin in these two different exchange. And if we see this timeline, we are saving a lot of time, a lot of dead time in each request, because every time that a Goroutine is blocked, is executed another Goroutine. So each time that you have to need different resources from different API with some wait times in the middle of this request, you always will have to apply concurrency, because will save you those dead times in each request. And for the other hand, if you have a program that needs a resource, but this resource it's very important because with this resource you will get another resources, and again, well, here maybe you don't have to apply concurrency because you will need first a resource, and then with this resource you can be able to get another resources. So imagine this situation where you apply concurrency. In this case, for example, you need the resource A and the resource B, but to get the resource B, you first need the resource A. So you apply concurrency, and well, this Goroutine will execute. We'll try to get the resource A. Here, the Goroutine will be blocked, so we have to wait for this API call. And this resource B, this Goroutine, sorry, will try to execute, but it will be blocked again because this Goroutine needs the resource A to make this API call. So it's better to use sequential programming here because it's the same, and the only thing that concurrency apports here is complexity on the code, because the time that we have to wait here is the same because the resource B depends on the resource A. In this case, it's better to use just a simple sequential programming. Well, now we will see some example of this with code. So first of all, I want to tell you that you will have all the code of this video here in this repo, where I explain you all about concurrency and synchronization and Goroutines and whatever. All the things that you will see in this video, you have it here on this GitHub repo, that the link will be in the description of the video. So here we have a main function that execute this function with concurrency. This is the function. And this function, well, will generate 10 Goroutines that will be executing in a concurrent way. And that Goroutines, all of these Goroutines, will execute this function to work. And this function, what it does is increment this pointer of integers by 1 and then wait for 1 second. So here we have a for loop that will execute 10 Goroutines with this body in the function. So each Goroutine will execute this do work function. To execute Goroutines in Golang, well, any concurrent method in another programming language, we will need to use some synchronization methods to synchronize our Goroutines or sub-process to make them work properly. So here we use wait groups, that is a synchronization mechanism. That what this wait group does is like a counter. Here we increment by 1 the counter of this wait group, and well, here we will be waiting to this counter of the wait group to be 0. With this differ function, we are telling here that every time that the Goroutine ends, execute this function, wait group that done. What it does is reduce this counter by 1. So here we add 1, 2, 3, 4, 5 until 10. And every time that a Goroutine ends, well, with this differ function, with this wait group that done, the counter will be reduced by 1. And when the counter of this wait group gets on 0, well, we'll execute the rest of the code of this function. So first, we will see how this with concurrency function works. So I will execute this, go run main.go. Well, this function is executed in 1 second, and it's telling me that the balance is 10. Okay, so we can think about it, because this function do work have a wait time of 1 second. So every time that this do work function is executed, this function have to wait for 1 second. But we are executing this function 10 times, and we just wait 1 second. How we can do that? And well, that is because we are using Goroutines in this case. So there are 10 Goroutines executing in a concurrent way. So this Goroutine is executed and it's blocked because you have to wait 1 second. So the Goroutine number 2 is executing, increment the balance by 1 and it's blocked, execute the number 3 and so on. So at the end, all the Goroutines will execute in only 1 second. When if we use this another function that is without concurrency. We are doing the same, but without wait groups, without a synchronization mechanism, because we are not applying concurrency here, but we are calling to this do work function. I'm passing here the pointer to this balance variable. So now we will execute this function and we will see the difference with this another function. I will let here the result of the with concurrency function to compare it. So here I will execute this another function and we just have to wait. And well, we get here that this function without concurrency executed in 10 seconds. So here we wait for 10 seconds to get something that with concurrency we can get it in just 1 second. The difference is huge. So every time that you can apply concurrency, you have to do it because it will save you a lot of time. So you have to know that every time that you need to get independent resources, you can apply concurrency and you will be benefit of the concurrency, because in each dead time when you apply concurrency, we'll try to execute another things and another things to make that works. But we have to apply concurrency in a smart way. Not always concurrency it's better, because in some situations applying concurrency, the only thing that will apport to us is complexity to our code. So we have to be careful and be smart when to apply concurrency. We have to apply concurrency when we identify that the resource that we want to get and we need to get to make this program are independent each other, and also each resource have a dead time in each request. Why we need wait groups? Well, wait groups are here to wait Goroutines. So imagine this situation. We are a Golang program and we execute two Goroutines to work concurrently. So this Goroutine will get the resource A and this other Goroutine will get the resource B independently, okay? But our main program, how knows that this Goroutine ends or this Goroutine ends? Because this main Goroutine will have to wait for those Goroutines ends. But how this main program knows that? Well, that's where wait groups came. Wait groups will allow to this main Goroutine, to this main program, to wait for all the Goroutines that this main Goroutine execute. So with wait groups, this main Goroutine can wait for this resource and this other resource. Well, now we will see this on code. First, I want to tell you that all the code that you can see in this video, you will have it on this GitHub repo. I will let the link on the description of the video so you can check it, and well, I recommend that you have it close to you while you are seeing this video, because it will help you to understand better all the things that I am explaining to you. Well, here we have three functions: do work function, with wait groups function, and without wait group functions. First, we will focus on these two, without wait groups and do work. So what this function does? Well, this function without wait groups, the only thing that it does is generate 10 Goroutines that will do this function, do work. What this function does? Well, this function, the only thing that does is wait 3 seconds and then print the number of this Goroutine. For example, the first Goroutine will print Goroutine number 1, the second Goroutine number 2, and so on. And after that, well, this function without wait groups will print. So I will execute this function first without wait groups to see what is happened. So go, and we can see that none of all the Goroutines that we execute here are printed on the console. Why is that? Why it seems like none of these Goroutines executed? Well, that is because we are not given time to those goroutines to execute. Because every goroutine have to wait 3 seconds. And after we execute this 10 goroutines, we finish the program basically, because we just have to print a message and then finish the main function. And when finish the main function, all the goroutines, bye bye. So we have to here wait for those goroutines that we execute before. So we can here put a time sleep and see what happens. So here we will execute the 10 goroutines, and then we will wait for 3 seconds, and then we'll execute this message. So I will execute this to see what happened now. And well, we are waiting here 3 seconds, and then finish the without wait groups function. But here are printed 3 goroutines. Okay, so 3 goroutines were executed before this final line, before this main function ends. If here we wait for 4 seconds instead of 3, we will have to see all the goroutines finished, and then the without wait groups function finish. So we will execute this. We will have to wait for 4 seconds, and then all the goroutines are executed, and then the without wait groups finish message. Why is that? Well, because we have to wait to our goroutines that we executed finish properly. But we can't use this time sleep here to wait for our goroutines, because, well, here we know the duration of each goroutine, that is 3 seconds. But normally we will not know how long will take a goroutine. So we have to make another thing, implement another mechanism to wait for our goroutines, to finish properly. So here comes wait groups. Wait groups are here to wait for our goroutines. So here we declare a wait group variable, and then every time that we are creating a new goroutine, we just have to make this wait group that add function that will increment a counter that is inside of the wait group. And then when we want to wait, before to do that, I want to make sure that all the goroutines that I execute before are finished. So at this point of the code, for example here, I want to wait for those goroutines ends. So here I execute this function, wait group that wait, that is a function associated to this structure. And this function, what it does is wait for this counter that I mentioned before, that we are incremented here, comes to 0. But how this counter comes to 0? Well, here, when I execute this goroutine, I am declaring here a different function that what it does is, when this do work function of this goroutine ends, okay, at the end, we'll execute this wait group that done. This wait group that done, what it does is decrement the counter by 1. So every time that a goroutine finish, we'll execute wait group that done, and with this, we'll decrement the counter by 1. So here, we just have to wait that all the goroutines end to get the counter on 0, and then, well, we just have to print this message safely, because here we already know that all the goroutines takes the time that takes every goroutine will end. So we don't have to be worried about how long takes every goroutine, because with these wait groups, we know that if we go to this line, all the goroutines are done. So I will execute now this function with wait groups to see what happens. So I will execute that and see. Well, we are waiting here the time that we have to wait, and then all the goroutines will be printed because all the goroutines are executed properly. And then when all the goroutines finish it, well, we print this message to end the main function. Well, the first goroutine that executed is the goroutine number 8, the second one, the goroutine number 1, the third one, the goroutine 0. So the first goroutine And well, here we also see that we don't have the control of our goroutines. When we apply concurrency, we lost the control of our program. So look at this. The coroutine number 8 is the first one on execute in this particular case. If I execute this again, maybe the first coroutine will be another one. Here is the number 9. We lost the control of our program, so we have to apply synchronization mechanism to make our programs work in a way that we want, because maybe we want to execute, I don't know, the coroutine number 7 first. And well, we can apply synchronization mechanism to do that. There are a lot of synchronization mechanisms. This is one of those. Another synchronization mechanism are channels. Channels allows to goroutines to put some message on a channel, and another goroutine will be listen for that channel, and this another goroutine can get the message from the other goroutine. It's a way to communicate two goroutines. Okay, so here in this diagram we can see like this goroutine put a message on this channel of integers, because every channel have to have a type, a specific type. Can be an struct, but have to have a type. If there is a channel of integers, we cannot put here strings. And the same for structs. If we have a struct of name, I don't know, dog, we cannot put on the channel of dogs another type of structure like cats. So we have to respect the type of each channel. In this case, it's a channel of integers, so this goroutine will put here a number, an integer, like for example 5, and this other goroutine will be waiting for that message. So if this goroutine comes first and well, there is no messages here on the channel, this goroutine will wait until this other goroutine puts the message. So this goroutine that is listened to this channel can be blocked by the channel itself, because if there is no message, this goroutine will be blocked and will not execute until get this message from the channel. But if this goroutine puts the message first, well, this other goroutine will get the message immediately and will execute with the other things that this goroutine have to do. So we will see this on code. I remind you, like always, that you will have all the code that you will see on this video, on this GitHub repo, which the link will be on the description of the video. So I recommend you that you have it closer to you while you are seeing this video, because it will help you a lot, okay? So going to the code. Here we have 6 functions: a producer, a consumer, and a with channel function, and another function that emulates the producer and the consumer, but this function is without channels. So first, we will see the without channels function to understand how we will have to implement these methods if we are not using channels. So first, look this function. In this function, we are using wait groups. I tell you that we will use wait groups in every method that we implement with goroutines. When we apply concurrency, we will have to use wait groups. We have here a resource variable. Well, this resource variable, we will pass it to these producer and consumer functions. These functions will execute in the background using goroutines. So this without channel will execute 2 goroutines, one to produce numbers and the other to consume those numbers, like we are seeing this here, but without using channels. So how we will do that? Well, we will do that using this variable here. And well, the producer function, what it does is generates a random integers every 3 seconds. So this is a for loop that never ends, but every 3 seconds generates a random integers, because here we are waiting for 3 seconds. And the same here on the consumer function. We are reading the number of this resource variable that we pass here, the pointer of this resource variable, and then we are waiting 2 seconds instead of 3. And that's because I want to show you that this consumer can print the same message twice, because maybe the resource are not updated by the producer function. In this mechanism, without using channels, maybe this variable or this resource that we have to producer and consumer, well, maybe the consumer consumes twice the same data, and we don't want that. But that are the risks to not use channels in this situation. So I will execute this function without channels to see what happens. Here the consumer reads 0, then the consumer reads 22, the consumer reads 43, 99, 99 again. So here is the example that I mentioned before, where we're using this without channels, a consumer and producer functions using a variable is dangerous because the consumer can consume the resource, the same resource data twice. So we have to use channels here because it's more simple and more safe. So we will see now the difference between the without channels function and with this other function that is with channels. So here we can see what it does, this function. Well, first, always we will need a weight group like so, and then we create a channel of integers. To create a channel, we have to use this, and here we have to put the type of the channel. In this case, it's an integer, but can be a string, a float, or any type that you like. Here we are telling to the wait group that we will execute 2 goroutines, and we will have to wait for those goroutines. And well, here is the same of here. We create 2 goroutines to execute a producer and consumer function. But here, instead of writing on the pointer of this variable, here we are writing to a channel, like so. The producer creates a random integer between 0 and 100 and put on the channel, like so. To put things on channels, we have to use these sentences. It's weird, but with time, it becomes normal. And then, well, we just wait for 3 seconds like we do here also. And the consumer, well, the consumer will create a variable n with the value of the channel. So here we are waiting. This consumer function will be blocked if there is no content inside of the channel. Will be blocked until the channel have something. So when the channel have something, some integer, we'll create this new variable n with the value that gets from the channel. So for example, if the producer function produce a number 5 and put that number to this channel, well, this consumer will read that number 5 from the channel and put here on the variable n, and then will print this number. Look that our consumer doesn't have to use a time that sleep to wait for the other number that our producer will provide us. We just have to print, and then we just have to wait here on the channel without using any time sleep. And it's better because maybe we don't know how long it will take to produce a new number on the producer function. So here, well, we just have to print every time that we can get something from this channel where the producer will be putting here new numbers every 3 seconds. It's like you can see here. This is the Goroutine producer that will put here numbers on the channel, and this is the Goroutine consumer that will consume the numbers that this Goroutine producer put here. So this Goroutine will get the number and print it, get the number and print it. If there is no number, well, this Goroutine will have to wait here to get a new number from this. But this can produce deadlock. That is another problem applying concurrency. But deadlocks and all the problems that generates concurrency and this synchronization mechanism, it's for other section. So now I will execute this with channel function to see what happens. It's the same that we see before, but now the consumer will never consume a number twice. Well, can consume the same number twice, but that is fault of the producer function because the producer can produce the same number in a row. Well, here we have an example. This example is the same example that you will see on the GitHub repo. Well, to implement select statement, why we have the need to implement a select statement to synchronize Goroutines? Well, here in this example, we have 3 channels. First, look this diagram to understand better the situation. We have 3 channels. Our program reads data through these 3 channels. A channel of integers, a channel of floats, and another channel of strings. So our program can read an integer, floats, or a string and do something with that data. Okay? So if our program receives an integer, well, our program will have to do something. If our program receives a float, okay, our program will have to do something else. And the same logic for the strings, okay? So we have 3 channels and we have to be listened of these 3 channels. If in this case we decide to don't use a select statement, we will have to create 3 goroutines specifically to listen every channel. One goroutine to listen the channel of integers, another goroutine to listen the channel of floats, and other goroutine to listen the channel of strings. And every time that a channel gets data from that channel, this channel will have to communicate to the main process and notify that, okay, this main process have to execute something with that data. But like we want to execute while we receive data, we will have to apply another synchronization mechanisms like mutex or something like that to synchronize, okay, this came first, I have to do this first, and later, when finished with that task, I have to do the following, and so on. So it's a lot of logic for not implemented a simple select statement in this particular case. So with a select statement, it will look something like this. We have 3 channels or 3 channels, a channel of integers, the float, and strings. There will be some goroutines that will dedicate to put data through those channels. For example, a goroutine that puts some integers here, another goroutine that puts float numbers here, and other goroutine that puts strings to this channel. But we will have just one goroutine to listen for all the channels. And the first data that comes from any of those channels, we will handle that and do whatever that we want to do with that data. For example, if I receive an integer, I want to multiply the integer by 2 and then print on the console, for example. And if I receive a float, I want to divide that float number to 5 and then print that number on the console. And if I receive a string, well, I just want to print that string on the console. It's just an example, but there is different functions to execute for every data type that we receive. So here, this goroutine will listen to all of those channels, and the first data that comes to that select statement, because this will be a select statement that will listen for all of those channels, well, will execute the logic of that particular data type or that particular channel, because here we are saying that, okay, this channel is for integers, this other channel is for floats, but maybe there are 2 channels dedicated for integers, but for example, a channel is for ages and other channel is for prices, and both channels contains integers, but those channels have different meaning. So it's the same. The point is that every channel will have a case in the select statement. So if we receive data through that particular channel, the select statement will handle that and will execute the functions associated with that particular data type that we receive, and will handle that in a very easy way. So now we will see this particular case on code. So here we have these 3 channels, the channel of integers, the channel of floats, and the channel of strings. And well, we have here 2 functions. One to execute producers. These producers are 3 goroutines that will produce integers every 3 seconds, floats every 3 seconds, and strings every 3 seconds. Here are the functions. This will produce a random integer and put that random integer to the channel using these sentences. Here we produce a random float and then put that float to the channel of floats that we receive here as a parameter, and then wait for 3 seconds. And well, the string it's more complex, but we generate a random integer from 0 to 100 and we convert that number to a string, and then we get the bytes of that string and Well, with the bytes, we get the hash of that particular string, and we put that hash to the channel of strings. And well, that's all for the producers. The producers are just 3 goroutines that will never end because there is a for loop every time in each producer function, but with a wait time of 3 seconds in each one. So that's for the producers. But the consumers, when we execute the consumers, well, here we have the select statement because this is the consumer here. So the consumer obviously have a for loop, but I will explain that later. But the main important thing is here in the select statement. In every case, we create a variable called data, that this variable will contain the data from a channel. Can be from the channel of integers, can be from the channel of floats, and can be from the channel of strings. So the select statement here is telling us, okay, if I receive for any reason, I've received an integer from this channel, I will put that integer on this variable data and will execute all the functions that have this case. If we have here more than one function, okay, we'll execute more than one function. We'll execute all the functions that we put here. But for this case, we just have one function to execute when we receive an integer. The same for the float. So if for any reasons this channel receive a float, the select statement will create a variable called data and will put here the float that we get from the channel. The same for the string. We'll create a variable called data with the string that we get from the channel. But while we are not getting any data from any of those 3 channels, the select statement will be blocked until some of these 3 channels can get some data. So be careful with that because maybe can produce a deadlock. Because if there is no other goroutines or something that put data to any of those 3 channels, there is a deadlock because this will never execute and will be blocked forever. And why we put here a for loop, a for end loop, because this for loop will never end? It's because we want to be listening every time, always, for new data that comes to these 3 channels. Because the select statement will listen for the first data that comes to these channels. So these channels doesn't have data. This other channel also doesn't have data, and the string channel doesn't have data. Okay, the select statement will be waiting for the first data that comes. And for example, if comes a float, the select statement will execute and will finish. So to be listening again, to be waiting again for some new data, I aggregate this for loop because every time that the select statement executes, then we'll execute again because of the for loop. And the functions that we use here is just for this particular case to show an example, but can be more complex functions where we receive an integer and we, for example, have to buy something or have to do something more complex than just print the number on the console. But for this purpose of the video, I just decided to print this with this particular signature to identify which function is. In this case, well, print integer, print float, and print the string. So we can identify on the console, okay, there is executing this function because the select statement received that particular string or that particular float or integer. So now I will execute this select function to see what happens on the console. And well, here we have the first data printed by the consumers. The producer of integer produced 52, the producer of strings produced this hash, and the producer of floats produced this float. 27 with 69. We can execute this again to see all the data all the data printed by the consumer, but there's a lot of data. Every 3 seconds will be printed again and again and again, new data. And you can see that not every time we get the same order of consumers executing. And that's because we lost the control of our programs. We cannot decide now when the producer will produce something. That's because we are working with concurrency, with Goroutines. But maybe the producer of integers produce an integer and then wait for 3 seconds, and then the producer of floats produce another float, and then instead of execute the producer of strings, it's executed the producer of integers again, and so on. We lost the control of our program. So that's because we have to use synchronization mechanisms when we apply concurrency, not only in Golang, in all the others programming languages every time that we work with concurrency, we have to apply synchronization mechanisms to make our programs work properly. Another synchronization mechanism that is very important to us is the mutex. With mutex, we can synchronize the access of multiple Goroutines to the same resource, to the same variable. Let's look an example on this diagram. Here we have two examples, a without mutex example and a with mutex example. First, we will look this without mutex example. So here we have two Goroutines that wants to read and write this particular variable that is balance. So these two Goroutines wants to access to the same resource, to the same variable that is balance. And the Goroutine number 1 and the Goroutine number 2 wants to do the same, that is read the balance, read the value of this particular variable, and then increment that value by 1. So imagine this situation like you can see here on the timeline, where these two Goroutines are executed in this particular way, where the Goroutine number 1 executes first, and well, this Goroutine read the balance of this variable, and at that particular moment the value of this variable was 0, okay, and then well, the operating system quick that Goroutine for any reason and put the Goroutine number 2 to execute. So the Goroutine number 2 at this particular moment reads the value of this balance variable, and well, at that particular moment the value of that variable was 0, and well, then ends and well, increment the value of that particular variable by 1. So at this moment the value of the balance variable is 1, but then the Goroutine number 1 executes again, and well, this Goroutine only left to increment the variable by 1. So like this Goroutine reads at this moment that the balance variable has a value of 0, at this moment this Goroutine will want to increment by 1, so will increment from 0 to 1 instead of what we expect, that is from 1 to 2, because at this moment the balance variable has a value of 1. But here the Goroutine number 1 doesn't know that. This Goroutine only knows that at this moment was 0, so the Goroutine number 1 expects that at this particular moment the balance value is 0, 2, like in this moment. But other Goroutine changed the value, and the Goroutine number 1 doesn't know that. So with mutex, we can synchronize that access to this particular variable. So we can be sure that when we read and write data, we are doing that in a safe way. So here we have this diagram where I try to show you how it will do the same but with mutex, applying this particular synchronization mechanism that is mutex. So here we have our two Goroutines that wants to read the balance and then increment the value by 1, like we have it here. But here we are applying mutex, this synchronization mechanism. So our two Goroutines will have to ask to this mutex, can access to that data, can access to that resource. And the mutex is like a semaphore. We can get a green light or a red light. At the first time, the mutex will be always on a green light. We can be able to access to this critical zone, that is this. But when a Goroutine gets into that particular critical zone, the mutex will be blocked. It's like the semaphore will put on the red lights. So if this Goroutine, the Goroutine number 1, access to that resource first, when try to get access to the same resource, it will be blocked because another Goroutine is already using that particular resource, and we don't want to multiple Goroutines use the same resource at the same time. So this Goroutine, if the Goroutine number 1 gets first, the Goroutine number 2 will be blocked here because this Goroutine has the entire access to that particular variable. So this Goroutine will have to wait that this Goroutine ends to use this particular resource, and when this Goroutine finishes to use this particular resource, here this Goroutine will unlock the mutex. It's like we put the semaphore on the green light again, and we continue doing something else but without using this particular resource. And then here the other Goroutines, can be more than one, finally can access to this particular resource, because this mutex at this moment, the mutex will be on green light again, and this goroutine will can access to that particular resource and put the semaphore on the red light, so other goroutines can't access to that particular resource at the same moment. So to understand better this particular situation, we can see here this timeline. Like we have it here, well, but with mutex, always we'll look at this timeline. So here, first, imagine that the goroutine number 1 execute first, because the only thing that can change in this timeline is the order of the goroutines. If here is the goroutine number 1, well, can be the goroutine number 2. If here is the goroutine number 2, well, can be the goroutine number 1. So here, the goroutine number 1 execute first and lock the mutex. So put the mutex on the red light for the other goroutines. And read the balance of this particular variable and read 0, because at this moment, the value of this variable is 0. Okay. Then the operating system quit that goroutine of executing and put the goroutine number 2 to execute. This goroutine try to lock the mutex, try to get access to this resource, but this goroutine cannot lock the mutex, cannot get access to that particular resource, because it's already blocked by another goroutine. So this goroutine will be blocked here until the mutex gets unlocked for the goroutine that lock the mutex. So then after that, the goroutine number 1 executes again, and well, like the goroutine number 1 already read the balance of that variable, this goroutine, the only thing that they have to do is increment that value that reads before by 1. So the goroutine number 1 increments the balance by 1, and then finally unlock the mutex. When this goroutine unlock the mutex, well, the goroutine number 2 will access to this particular balance variable and well, will read the balance and will read 1, because at this moment when the goroutine number 1 ends, the balance of this variable will be 1, and well, this goroutine number 2 will increment from 1 to 2, and that's what we want. So now we will see this on code. I remind you that you will have all the code that you will see in this video in this particular GitHub repo. In this repo, I put all the code of all of the synchronization mechanisms that I am sharing with you in my YouTube videos. So I recommend you that you have it close to you while you are seeing my videos, because it will help you to understand better all the things that we are doing on the video. So now we will see this example in code. So here we have 3 functions: a do-work function, a with mutex function, and without mutex function. We want to emulate this particular situation where we have multiple goroutines that wants to access to some variable and increment it by 1. And we want to do that using mutex and not using mutex to see the difference between these 2 implementations. So first, we will look the without mutex implementation. So this function, what it does is, well, creates a variable called balance and initialize that variable on 0. After that, we execute 10 goroutines that these goroutines will do this do-work function. This do-work function receives a pointer to this balance variable and then a flag, with mutex flag that, well, this flag will say to us, to this function, if wants to apply mutex or if not want to apply mutex. So for this particular case, we pass here false to not apply mutex, and well, we here dereference the pointer of this variable and increment it by 1 using this syntax, and then we wait for 1 second in the do work function. So we execute 10 goroutines that do this particular thing. So we expect that the balance variable at the end of this program, it's 10, because we execute 10 goroutines that all of one increment the balance by 1. So we expect that at the end of the program, the balance variable will be 10. But you will see on this code that not every time it's 10. The majority of the time it's 10, but in some situations it's not. And that's for the race conditions that we provoke here when we don't use mutex or any synchronization mechanisms to handle that access of multiple goroutines to the same resource. So because of that, I want to show you that in some cases the variable balance will not be 10, I do this for end loop where I will repeat this process of execute 10 coroutines until I get finally a balance different from 10. And if this function gets a balance different from 10, well, we'll print that balance number on the console. And then we'll execute again. We'll try to find another case where the balance is different from 10, and again and again and again. It's a for end loop. So we will execute this. So here we have to wait until, well, here we have two examples now of that we are executing this function, but we are getting a balance difference from 10. In these two cases, we got 9 instead of 10, and that's for the race conditions. Here we have now 5 cases, 6 cases of race conditions in this particular execution of without mutex. So you can see that if we don't apply synchronization mechanisms in some cases where when we apply concurrency, it's dangerous, because if we execute this function once, maybe we get 10 as a result, and maybe we think it's okay, but it's not okay, because in some cases will not produce the same value, the same results, and it's dangerous. It's totally dangerous. So now we will see the implementation of this using mutex, and then we'll execute the function with mutex to see the difference between these two implementations. So the function with mutex, it's the same that this function, but here, well, we just execute this once. We don't execute this forever, because forever will be the same results. The balance always will produce the balance tens, because always will produce the same results. The balance variable will have the value of 10. It will never get some different value of 10, because we are applying mutex. With mutex, we guarantee that. So here, well, we execute 10 Goroutines using the same logic here, and the only difference is that here we pass the flag on true. So here in the do work function, we'll execute this part of the if statement, and here we'll apply mutex. So it's like we see before on the diagram. When a Goroutine get access to the mutex, okay, we'll ask to the mutex, can access to the resource, or I have to wait? If there is no Goroutine using that particular resource, the mutex will respond to the Goroutine, no problem, came and use the resources, because none of those Goroutines are using the same resource that you want to use, so came and use it. But if there is already a Goroutine using the resource that we want to use, the mutex will say to us, wait here until the other Goroutines that are using this resource ends. Okay, I wait. So here, with this sentence, we ask to the mutex, can I access to the mutex? If the mutex is already used by other Goroutine, will be blocked here. But if it's not, if any Goroutine are using this particular resource, we will be able to access to that particular resource, and well, for this moment, all the other Goroutines will not be able to access to this particular resource, to this particular critical zone, because we already are inside of this critical zone. So the other Goroutines will be waiting here until our Goroutine that gets this resource, that lock this mutex, doing the following, that is unlock the mutex. When we unlock the mutex, we'll put the mutex on the green light again, so other Goroutines can be able to access to this particular resource. And that's all, because with this we are guaranteed that all the Goroutines that wants to get access to this particular resource, access to this particular resource in a safe way. So now I will execute this function with mutex to show you that always we will get a result of 10. So I will execute this, and well, we get it here 10, I will execute this again, and well, we get 10 again. I will execute again to see what happens, but it will show me again 10, because always we will have the same results when we apply asynchronization mechanisms like mutex to this particular resource that all the goroutines want to access at the same time. So when we have to apply mutex, well, we have to apply mutex when we know that multiple goroutines will want to access to the same particular resource. If multiple goroutines want to access to the same particular resource in any time, it doesn't have to be at the same time or to do the same, because maybe we have another goroutine that do another work, another things with this variable of balance, but it's the same. If more than one goroutine get access to the same resource, we have to apply mutex. We have to, because if we don't apply mutex or some synchronization mechanism that allow us to be sure that when a goroutine get access to this particular resource, this resource will be safe from that moment until the moment that this goroutine ends or ends to use this particular resource. We have to be sure that, because if we don't be sure of that, we will not be sure about our programs, because our programs can produce race conditions or some other concurrency issues. So we have to be sure about that to don't provoke any of those concurrency issues. Other synchronization mechanism that we will see is the atomic. Well, this will be the last synchronization mechanism that we will see. Atomic is very similar to mutex. With atomic, we guarantee that only one goroutine can access to some resource. It's very similar to mutex. Here in this diagram is show you how works mutex, but for this case it's almost the same, because with atomic we guarantee that this resource, this balance variable, get access by only one goroutine, only one concurrent process at the same time. So if one goroutine, one concurrent process are using this variable or this resource, all the other goroutines cannot access to that particular resource. So at the end is the same that mutex, but with different sentences to declarate this synchronization mechanism. So like it's almost the same as mutex. Well, with mutex we want to prevent race conditions in our program. So with atomic it's the same. We use atomic to prevent race conditions in our program. So I will explain you the same case that I explained you on the mutex, but I have to explain this again for those who don't see the mutex section. So where here we just have two goroutines that are working concurrently. These two goroutines want to do the same, that is, read the balance variable and then increment it by 1. But these two goroutines are executing without a synchronization mechanism. In this case, mutex or atomic. So these two goroutines doesn't have any synchronization mechanism to access to this particular variable. So here on the timeline, we can see that maybe our goroutines execute in this order. And if execute in this order without a synchronization mechanism, we have here a race conditions, because here our goroutine number 1 reads the balance of this variable, because here our goroutine number 1 reads the value of this variable and gets 0, because at this time it's 0. Then this goroutine quick and get into execute the goroutine number 2. The goroutine number 2 also read the value of this variable, and like at this time it's 0, read 0 too. And well, this goroutine doesn't quick, so this goroutine ends and well increment the value of this variable by 1. And after that, the goroutine number 1 goes back to execute. And well, this goroutine already reads the value of this variable. So this goroutine already know that this variable has a value of 0. And then, well, this goroutine will end incremented this value by 1. So we'll increment from 0 to 1 instead of what we expect, that is going from 1 to 2, because at this moment this variable has a value of 1. But this goroutine, like this goroutine reads here the value of this variable, this goroutine doesn't know that in the middle another goroutine increment the value or do something with the value of this variable. So to prevent that, we have to use a synchronization mechanism. We can use mutex or, in this case, atomic. I will show you an example of how to use atomic in code. So here I have, like always, three functions: a do work function, a with atomic function, and another function that is without atomic. I want to show you the difference between using atomic and when we don't use atomic, and well, when we don't use mutex2 or any synchronization mechanism. I want to show you the difference between using synchronization mechanism properly and when we not use synchronization mechanism, what happens in the cases where we working with concurrency, because all of this will never happen if we work in a sequential way. All of this happens when we try to execute multiple goroutines, multiple processes in a concurrent way. So first, I will show you this without atomic function, what it does. Well, this is a for and loop, so we'll execute every time. And well, here we'll execute 10 goroutines, and these 10 goroutines will try to increment the value of this balance, that initially it's 0, by 1. So at the end, this variable must have a value of 10. But what happens when we don't use a synchronization mechanism like mutex or in this case atomic? Well, in some cases the value of this variable will not be 10, will be different from 10. And that's because the race conditions that we provoke here. So first I will show you this so you can see that I am telling you the truth, that in some cases this balance will not be 10. And well, I forget to show you this do work function. Well, this do work function will receive a pointer of this balance and this flag that is with atomic, that is a Boolean variable that, well, will help me to decide in this function if I use atomic or if I not use atomic. So if in this case without atomic, I just pass here false. So in this case execute this code, and well, this code doesn't use synchronization mechanism. It's just trying to get into that particular variable and increment the value from there. Like we can see here, we doesn't have any synchronization mechanism. The goroutines are trying to execute directly from the resource, and that is dangerous because can produce race conditions, and it's what we want to see here. Well, if we pass here true, well, we'll execute this part of the code, that is the atomic part, where we apply this synchronization mechanism. But I will explain that later, once we see first this with atomic function in action. So here I will execute this without atomic function to see what happens. So this function will execute every time looking for, in like this case, a balance different from 10. The majority of the time we'll find a balance of 10, but that is the dangerous thing here, because race conditions are not always telling us you have an error here. No, it's in some cases depending on how these goroutines are executed. So here I am getting a lot of values different from 10, and that's because this without atomic function is executing in a for and loop. It's executing every time looking for new balance difference from 10. But well, I have to shut down this function because it will execute forever if I don't shut down this function. So I will shut down this function, and then I will show you the difference between this without atomic function and this with atomic function. Well, here with this atomic function, it's almost the same that we have here, but without the for and loop, and that's because here always we will get the same results because we are applying synchronization mechanisms, in this case atomic. So it's the same. This function executes 10 goroutines, and these 10 goroutines will try to increment this variable of balance by 1. So at the end, the variable of balance will have a value of 10, but in this function always will have a value of 10, and that's because we are using synchronization mechanism. In this case, we are using Atomic. So Atomic is a package that we import here, so we can use it. And here we have a lot of functions like this: add integer of 64 bits, add integer of 32 bits, compare and swap integers of 32 bits, compare and swap integers of 64 bits. And well, we have here a lot of functions that we can use from this package of Atomic. All of those functions of this package of Atomic will guarantee us that we are executing this in a safe way. But for me, Facundo, I prefer to use mutex instead of this Atomic, because with mutex I feel like I have the entire control of when a goroutine can access to some critical zone and when not. But that's what I feel. Some people maybe like to use Atomic instead of mutex, but I like to use mutex instead of Atomic. And well, I just have to show you how this with Atomic function works, but it will show you a balance of 10 in every execution. So, well, I will execute this function to see what happens. And well, here we have a balance of 10, waiting 1 second. I will execute this again. And well, I get here 10 again. I will execute again to show you that I will get 10 again. And of course, I get 10. And that's because we are applying synchronization mechanism, because we are applying here Atomic. Race conditions are generated where multiple goroutines, multiple concurrent processes are accessing to the same resource at the same time. So for example here, like we see on the mutex example and also on the Atomic example, the only goal of these two goroutines is read the value of this variable and then increment it by 1. But these two goroutines are working concurrently. So here, if we don't apply synchronization mechanisms properly, we can invoke a race conditions between these two goroutines. For example, in this timeline, you will see this easily, because the goroutine number 1, in this case, executes first, and well, this goroutine starts to execute. The first thing that this goroutine do is, well, read the value of this variable. Once this goroutine reads the value of the variable, then the goroutine will have to increment the value by 1. But at this point, the operating system quick that goroutine and put the goroutine number 2 to execute. The goroutine number 2 start to executing, and well, the first thing that this goroutine do is read the value of this variable. And well, at this point, like this goroutine, this first goroutine doesn't increment the value of this variable, well, at this point have 0 as value, have the same value that have here. So the goroutine number 2 reads the value of this variable on 0. Then, like this goroutine is still executing, this goroutine will increment the value of this variable by 1. So at this moment, if we read the value of this balance variable, we will see that the value of this variable is 1. Okay. But when this goroutine number 2 ends, comes again the goroutine number 1 to execute. But like this goroutine, the only thing that have to do is increment the value of this variable that this goroutine already read the value. So here, the goroutine number 1, the only thing that will do is increment the value of this variable from 0, because 0 is the value that this goroutine reads here, from 0 to 1, because this goroutine increment the value of this variable by 1. So we'll go from 0 to 1, instead of what we expect, that is, at this point, this variable has a value of 1. So here, when this other goroutine increment the value by 1, 2, we'll go from 1 to 2. That is what we expect. But like here, there is a race condition. In some cases, the results of our programs will be different from that we expect, although the code is correctly. So because of that, we have to implement synchronization mechanisms properly. So now I will show you an example of this race condition on code. So here we have two functions, a race condition function and a do work function. This race condition function, what it does is execute 10 Goroutines, and all of those Goroutines will do this do-work function. This do-work function, the only thing that does is increment this resource variable by 1. So if we execute here 10 Goroutines and all of it wants to increment this resource variable by 1, at the end, when all of these Goroutines ends, we expect that this resource variable have a value of 10 because there are 10 Goroutines trying to increment this resource variable by 1. But we will see here like we are not applying any synchronization mechanism here to increment this resource variable, and this resource variable is accessing by a lot of Goroutines in a concurrent way. We are provoking here race conditions, so it will be some cases where this resource variable will not be equal to 10. It's the same example that we see before on the mutex and the atomic implementation. But here, like we are explaining race conditions, I have to repeat this example because remind that mutex and atomic synchronization mechanisms are here to prevent these race conditions. So here this function, this race condition function, will execute this for end loop until gets a balance different from 10. When this function gets a value on this resource variable different from 10, we'll execute this part of the code and we'll finish because we'll break this for end loop. So to show you this, I will execute this function. So you can see that it will be one case when this resource variable will have a value different from 10. And here is. We have it here, a balance of 9 when we expect a balance of 10. Other concurrency problem is deadlock. Deadlocks are generated when two or more Goroutines are trying to access to the same critical zone using mutex as their synchronization mechanism, but using that mutex in a bad way, like you can see here on this diagram. Here we have the Goroutine number 1 and the Goroutine number 2. Both of them wants to access to this value variable. It's an example very similar to this, because we have two Goroutines that wants to get access to some resource, to some variable. And well, here we have these two Goroutines that wants to get access to this resource, this value, but like we want to prevent race conditions, this other concurrency issue, well, here we apply mutex, a synchronization mechanism to prevent those race conditions when these two Goroutines trying to get access to this particular resource. So to prevent that, we use mutex. But here we are applying mutex in a bad way, because this Goroutine number 1 lock the mutex A first and then lock the mutex B, while this other Goroutine first lock the mutex B and then lock the mutex A. When we have this situation where two or more Goroutines are trying to get access to the same resource but with different order in their mutex, here we have a very clear situation of a deadlock. Because imagine this situation like you can see here on the timeline. The Goroutine number 1 executes first. So this Goroutine, the first thing that we'll do is lock the mutex A. Then, for any reason, the operating system quick that Goroutine and put the Goroutine number 2 to execute. The first thing that this Goroutine number 2 will do is lock the mutex B, and can lock the mutex B because there is no other Goroutine locking the mutex B. So can lock the mutex B. The operating system quick the Goroutine number 2 and put again the Goroutine number 1 to execute. So the Goroutine number 1 gets here, so left to lock the mutex B. And when the Goroutine number 1 will try to lock the mutex B, the operating system will tell to the Goroutine 1, wait, because the Goroutine number 2 already have locked the mutex B. So you have to wait until the Goroutine number 2 ends. Okay, the Goroutine number 1 gets here blocked until the Goroutine number 2 finish. But what happened? Here the operating system quick the Goroutine number 1 because it's blocked and put the Goroutine number 2 to execute. And well, when the Goroutine number 2 start to execute, the Goroutine number 2 will start here because the Goroutine number 2 already locked the mutex B. So The only thing that have to do now is lock the mutex A. And when this goroutine try to lock the mutex A, the operating system will tell to us, as a goroutine number 2, hey, you have to wait here because the mutex A is already blocked by the goroutine number 1. So you have to wait until the goroutine number 1 ends. Okay, but the goroutine number 1 also it's waiting. And why this goroutine is waiting? This goroutine is waiting because this goroutine needs something that have the goroutine number 2, and the goroutine number 2 is waiting too because the goroutine number 1 have something that this goroutine needs. So here it's a clear, simple situation of deadlock where two goroutines are provoke a simple deadlock. And that's it only because we use in a bad order the mutex. If we use the mutex A first here, if that was the case, the goroutine number 1 can execute completely, and then the goroutine number 2 will execute completely again. But like we use this particular order of locking this mutex, we are producing a deadlock. So now we will see this example on code. So here we have 3 functions: a goroutine A, a goroutine B, and a deadlock function. This deadlock function, what it does is generate 2 goroutines, a goroutine A and a goroutine B, and then wait until these 2 goroutines ends. But what's happened? If we are provoking a deadlock, these 2 goroutines will never end. So what this goroutine A and this goroutine B does? Well, it's the same that we see here on the diagram. The goroutine A will lock the mutex A first and then lock the mutex B, and the goroutine B will lock the mutex B first and then lock the mutex A. In some point, when these 2 goroutines execute this first line and try to execute this second line, will generate a deadlock. So when our program gets inside of a deadlock, it will exit immediately, so our program will finish. Because if our program will not finish, our program will be waiting forever. So now I will show you this to see what happens when we have a deadlock. So I will execute this deadlock function to see what happens. And well, here we have the deadlock. It's like an error, but our code, if we don't know what is happened, we see our code and we think it's okay. But the only thing that we have to change here to prevent this deadlock is change the order of the mutex A and the mutex B in one of these 2 functions, because we have to do the mutex lock in the same order always. So I will lock the mutex A first and the mutex B then. So here I have to make that. And for the unlock, I recommend that always follow the same order. So here we have to unlock first the mutex A and then the mutex B. When we use mutex, we have to be sure that we use it in the correct order always. Because if we don't follow the order in some cases, we can provoke a deadlock, and we don't want that. So if I fix only the mutex order and try to execute again, you will see that we'll execute correctly. So here we can see that the function ends correctly with a resource A value of 2 and also with a resource B value of 2. And that's because, well, our goroutines, each one increment the resource A by 1 and then increment the resource A by 1 and the resource B. So this resource value was incremented twice by 1. So when the function ends, we expect that these 2 resource values gets on 2. So it's fine. So the last concurrency problem that we will see is starvation. Starvation, when occurs? Well, starvation occurs in situation like this that you can see here on this diagram, where we have 2 goroutines that are looking to get for a particular resource, a particular variable, and to avoid race conditions, use mutex to synchronize the access of that goroutines to that particular resource. But how starvation occurs? Well, occurs when a goroutine or a concurrent process cannot access never to that particular resource. Occurs when a goroutine, a concurrent process, gets blocked forever in the mutex. And that's when happen. Well, happen when a goroutine get access to that particular resource, but will never unlock the mutex of that particular resource. Like you can see here, this goroutine number 1 access first to this mutex, so it's the first goroutine to get access here, and well, the mutex allow to this goroutine to access to this value, but this goroutine never unlock the mutex, never. So it will use this value forever until the main program ends. So this other goroutine, when try to lock the mutex A, the operating system will tell to the goroutine number 2, wait here, because the goroutine number 1 already have the mutex A locked for the goroutine number 1, so you have to wait here until the goroutine number 1 ends. But what happens? The goroutine number 1 never ends, so this goroutine will never execute, will never finish, because it will be waiting forever. So that's what happens. That is starvation. So we will see this on code now. So for this case, we have here two functions, a goroutine C and a function of starvation. Here we have a global mutex and a global value variable that is initialized on 0. The starvation function, who is the function that we will execute here, this function, the first thing that does is lock the mutex, this global mutex, and then execute this goroutine C in background in a concurrent way. And then, while this goroutine C is executing or not, this function of starvation creates a for end loop that will never end, and this for end loop will print starvation every 3 seconds, because here is waiting 3 seconds, and then will print again starvation and so on. And what does this goroutine C? Well, this goroutine C will try to lock the mutex, the global mutex, but will never can, because this starvation function, the first thing that does before to execute this goroutine C is lock the mutex, but never unlock the mutex. So here we have an starvation example, because this goroutine C will never execute. So if I execute this starvation function, you will never see this message of goroutine C value plus plus. The only message that we will see on the console is starvation. So I will execute this to see what happens. And here we are seeing our first starvation, our second starvation, and well, we can be waiting here forever because the goroutine C will never execute. And that's because the starvation. So to prevent that, we have to always lock the mutex and unlock the mutex. And this process of lock and unlock will not have to be outside of a for end loop, because we can use mutex in a for end loop, but the mutex have to be inside of the for end loop, because if we lock the mutex here and then we go inside of a for end, yes, we are locking the mutex correctly here, but we will never end this for end loop. So if we want to prevent, for example, the print on the console, we have to do this instead. We have to here inside of the for loop lock the mutex and then unlock the mutex. If we apply this, the goroutine C will execute correctly without problems, because the starvation function will lock and unlock the mutex inside of this for end loop. So every time that this for end loop executes, we'll try to lock, and when this function can lock the mutex, well, we'll print this, we'll wait for 3 seconds, and then we'll unlock the mutex. So in that particular case, when we unlock the mutex, we are allowing to other goroutines that can use this mutex too to enter to this critical zone and do wherever these other functions wants to do. So we will check this to show you that using this, the goroutine C will execute properly. So I execute this, and here the goroutine C executes. Like I always said, with concurrency, we don't have the control of our program, because we can think that the goroutine C, like is here, it will execute first that this, but you can see here that was executed twice, this for end loop, and then the goroutine C. So when we work with concurrency, we don't have the control of our programs. The order of our programs depends on the operating system now. But that's fine because concurrency improves the performance of our programs. But like always, I said, we have to be careful with concurrency because applying bad practice in concurrency, it's dangerous. It's very dangerous for our programs. So that's all. That's all for starvations. And well, that's all for this video. I hope that you could understand all about concurrency, synchronization, and concurrency problems in Golang. And well, if you like this kind of videos, I will ask you again that hit the like button and subscribe to my channel. It's free, so do it. If you have any doubts about this video or whatever, concurrency, synchronization, or concurrency problems, please let me know that on the comment section below, and I will respond you quickly. So that's all. I will see you on the next video.